Welcome to DAR Tutors, your expert resource for online and home tuition in IB A-Level and IGCSE curricula. In this video, we will explore the fundamental concepts of spontaneity, entropy, and the second law of thermodynamics. Our main goal today is to understand what drives chemical changes, the guiding question that this topic addresses. We will be focusing on several key learning objectives, all directly aligned with the IB Chemistry HL syllabus. First, you will be able to define entropy as a measure of the dispersal of matter and energy. This statistical understanding is crucial. Second, you will be able to predict the sign of the entropy change, delta S, for a variety of processes based on states in stoichiometry. Third, we'll learn to calculate the standard entropy change for a reaction using standard entropy values. Finally, we will apply the second law of thermodynamics, using the concept of total entropy change to determine the spontaneity of a process. We begin with the concept of spontaneity. A spontaneous process is one that, once initiated, will continue on its own without requiring constant external energy input. It's a process that moves a system towards its most stable equilibrium state. Let's consider a few examples to illustrate this. A classic physical example is the flow of heat. Heat flows spontaneously from a hot object to a cold object. We don't need a pump or work to make this happen. It's a natural tendency. This process increases the overall entropy of the universe. The reverse process, heat flowing from cold to hot, is non-spontaneous. While it is possible, it requires work, like in a refrigerator or a heat pump. Another example is the dissolution of a salt in water, such as sodium chloride. This is a spontaneous process that increases the dispersal of matter. It does not require continuous work to occur. In contrast, the electrolysis of water is a non-spontaneous process. The decomposition of liquid water into hydrogen and oxygen gas requires the continuous application of an external electrical potential. The moment the power supply is removed, the process stops. Therefore, it is non-spontaneous. However, it is crucial to understand the difference between spontaneity and kinetics. Spontaneity tells us whether a process can happen, but not how fast it will happen. Kinetics, which is covered in Chapter R2.2, studies the rate of reactions. For instance, the conversion of diamond to graphite is a spontaneous process under standard conditions, but it is so incredibly slow that it's unobservable in practice. This highlights the important distinction between what is thermodynamically possible and what is kinetically feasible. To understand spontaneity from a microscopic perspective, we need the concept of entropy. Entropy, symbolized as S, is a measure of the dispersal of matter and energy within a system. Essentially, it reflects the number of ways particles and energy can be arranged. Statistical thermodynamics formalizes this with the Boltzmann formula. Here S is the entropy, K is the Boltzmann constant, and W is the number of microstates. A microstate is a specific arrangement of particles and their energies that is consistent with the system's overall state. The more microstates, the higher the entropy. Let's make this concrete with a simple model. Imagine a system with only one unit of energy and two particles, A and B, that can store this energy in discrete levels, 0 units or 1 unit. If the total energy is 1 unit, the system could have particle A on level 1 and B on level 0, or particle B on level 1 and A on level 0. These are two distinct microstates, so W equals 2. This represents a system with some entropy. Now, let's consider the expansion of a gas into a vacuum. This is a highly spontaneous process. Imagine 5 gas molecules, labeled 1 through 5, confined to the left half of a container by a partition. When the partition is removed, the molecules can move freely into the entire volume. Each molecule now has 2 possible places to be, the left half or the right half. For these 5 molecules, the number of microstates, W, is 2 to the power of 5, which equals 32. This is the total number of ways the molecules can be distributed between the 2 halves of the container. Let's compare the initial state, where all particles are on the left, with the most probable state, where they are evenly distributed. The initial state is just 1 microstate out of 32. But how many microstates correspond to an even distribution, say, 3 molecules on the left and 2 on the right? This is a combinatorial problem, and the answer is 20. W final is greater than W initial, so S final is greater than S initial. Delta S is greater than 0. Since the number of microstates, W, increases dramatically upon expansion, the entropy, S, of the gas also increases. This demonstrates how entropy is related to the distribution of matter in space. The most probable macroscopic state is the one that can be realized in the most ways at the molecular level. This is why gases expand spontaneously. We can extend this idea of dispersal to predict the sign of the entropy change, ds, for various chemical and physical processes. The general principle is straightforward. If the products of a process are more disordered or have a greater dispersal of matter and energy than the reactants, the entropy will increase and ds will be positive. Conversely, if the products are more ordered or less dispersed, the entropy will decrease and ds will be negative. For molecules containing a similar number of atoms, gases have the highest entropy, followed by liquids, and solids have the lowest entropy. This is because particles in a gas are highly dispersed and move randomly. Liquids are less ordered, and solids are highly structured lattices. Let's apply this rule. Consider the melting of ice. In this process, a highly ordered solid, ice, transforms into a less ordered liquid, water. Matter becomes more dispersed, so the entropy increases. ds is positive. A key indicator for predicting the sign of entropy changes in reactions is the change in the number of gaseous molecules. When a reaction increases the number of moles of gas, it leads to a large increase in entropy, so ds is positive. For example, in the decomposition of calcium carbonate, a solid and a liquid produce a gas. This increase in gaseous moles means a large increase in entropy. Conversely, when a reaction decreases the number of moles of gas, entropy decreases, and ds is negative. In the Haber process, 4 moles of gaseous reactants form 2 moles of gaseous product, a net decrease of 2 moles. This results in a decrease in entropy. Here is an IB-style practice question. Pause the video and try to predict the sign of the entropy change for the following reactions. Predict the sign of the entropy change for these reactions. Let's review the answers. For part A, 2 moles of gas produce 2 moles of gas. The change in the number of gaseous moles is 0. Therefore, the entropy change will be very small, close to 0. For part B, a liquid transforms into a solid, a more ordered state. Entropy decreases, so ds is negative. For part C, a liquid produces a liquid and a gas. The formation of 1 mole of gas from no gas means a large increase in entropy, so ds is positive. Now let's learn how to calculate standard entropy changes quantitatively using data booklet values. The standard entropy, S0, is the entropy of 1 mole of a substance in its standard state, typically 298 Kelvin and 100 kilopascals. These values are absolute, unlike standard enthalpies of formation, which are relative. It's a common misconception to assume the standard entropy of an element is 0, like enthalpy of formation. This is incorrect. Entropy is only 0 for a perfect crystal at absolute 0, 0 Kelvin. All standard entropies at 298 K are positive. The standard entropy change of a reaction, delta S0, is calculated as the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants, each multiplied by their stoichiometric coefficients. N and M are stoichiometric coefficients. Let's work through an IB-style example. We'll calculate the standard entropy change for the combustion of methane. First, we'll list the standard entropy values, S0, for each reactant and product, which we would find in the IB chemistry data booklet. Here are the values we need: methane, oxygen, carbon dioxide, and liquid water. Now we apply our formula. The sum of the entropies of the products is S0 of CO2 plus 2 times S naught of H2O. The sum of the entropies of the reactants is S naught of CH4 plus 2 times S naught of O2. Notice we multiply the standard entropy of water and oxygen by their coefficients of 2. Plugging in the values, we get this expression. Remember, all these units are JK1 mol 1. Performing the arithmetic gives us a final value of negative 272 JK1 mol 1. This negative sign aligns with our prediction. The reaction starts with 3 moles of gas and produces 1 mole of gas. A decrease in the number of gaseous moles typically leads to a decrease in entropy. We have seen that spontaneity is not solely determined by enthalpy, dH, or entropy, ds, of the system. In some cases, a process is spontaneous despite being endothermic. This is a paradox we must resolve. The resolution comes from the second law of thermodynamics, which states that any spontaneous process leads to an increase in the total entropy of the universe. This is the fundamental criterion for spontaneity. This means we must consider both the entropy change of the system, ds system, and the entropy change of the surroundings, ds surroundings. Their sum, the total entropy change, ds total, must be positive for a process to be spontaneous. How do we calculate ds surroundings? It's not as simple as subtracting standard entropies of surroundings components because surroundings can be very complex. Fortunately, for a reaction at constant temperature and pressure, there is a simple and elegant relationship. The entropy change of the surroundings is directly proportional to the negative of the system's enthalpy change, and inversely proportional to the absolute temperature, T, in Kelvin. This formula makes intuitive sense. An exothermic reaction, negative DH system, releases heat into the surroundings, increasing their thermal motion and thus their entropy, leading to a positive DS surroundings. An endothermic reaction, positive DH system, absorbs heat from the surroundings, decreasing their entropy, leading to a negative DS surroundings. Let's apply this to another IB-style problem. This time, we'll calculate the entropy change of the surroundings. Consider the decomposition of nitrogen dioxide at 25 degrees Celsius. The key is to pay close attention to units. The enthalpy change is in kilojoules per mole, but our entropy change should be in joules per Kelvin mole. First, we convert the temperature to Kelvin. 25 degrees Celsius plus 273.155 gives 298.50 Kelvin. Next, we convert the enthalpy change to joules per mole by multiplying by 1,000, giving negative 58,200 J2 mol. Now we can use our formula. ds surroundings equals the negative of dH divided by T. This gives us positive 195.2 JK1 mol 1. Notice that because the reaction is exothermic, it releases heat, which increases the entropy of the surroundings. We now have all the tools to perform a full spontaneity analysis by calculating the total entropy change. Let's do another worked example. Let's analyze the condensation of water vapor on a window at 25 degrees Celsius. Our strategy will be to calculate ds system, then ds surroundings, and finally their sum, ds total. First, for the system's entropy change. The system entropy change is the product entropy minus the reactant entropy. This gives 70 minus 189, which is negative 119 JK1 mol 1. The entropy of the system decreases, which makes sense as the ordered liquid forms from the disordered gas. Next, let's calculate the entropy change of the surroundings. Again, be careful with units and temperature. 25 degrees Celsius is 298.75 Kelvin, and the enthalpy change is negative 44,000 JA mol. Plugging these in, we get positive 147.6 J, K1 mol 1. The exothermic condensation releases heat, increasing the entropy of the surroundings. Finally, we can determine the overall spontaneity. ds total is the sum of ds system and ds surroundings. Negative 109 ton plus 147.6 equals positive 28.6 JK1 mol 1. Since this value is positive, the total entropy of the universe increases, and we can conclude that the condensation of water vapor at 25 degrees Celsius is a spontaneous process. This result confirms what we observe in everyday life. Water vapor spontaneously condenses on a surface cooler than its boiling point. It's a spontaneous process driven by the entropy increase of the surroundings, which outweighs the entropy decrease of the system. Now, let's challenge ourselves with a series of IB-style practice questions to consolidate our understanding. Pause the video after each question to work through it yourself before watching the solution. This is the best way to master these concepts. Question 1 asks us to predict the sign of the entropy change for the dissociation of a molecule into atoms. Here's the solution. A single molecule is breaking apart into two separate atoms. This process increases the number of independent particles, leading to greater disorder and dispersal. Therefore, the entropy change, ds, is positive. So for this reaction, the sign of the entropy change is positive. Question 2 asks for the standard entropy change for the formation of ammonia. Let's work this through. The formula is the sum of product entropies minus the sum of reactant entropies. We have 2 moles of ammonia as product, so we use 2 times S0 of ammonia. For the reactants, we have 1 mole of N2 and 3 moles of H2. Performing the calculation gives 386 minus 585, which is negative 199 JK1 mol 1. This negative value reflects the decrease in gaseous moles from 4 down to 2. Question 3 asks us to choose the reaction with the largest increase in entropy. The best way to determine the largest increase in entropy is to look at the change in the number of gaseous moles. Reaction A has 3 moles of gas going to 2. Reaction C has 2 moles of gas going to 1. Reaction B has 0 moles of gas going to 1. Therefore, reaction B shows the largest increase in moles of gas, and thus the largest increase in entropy. The correct answer is B. An increase of 1 mole of gas from a solid is a significant increase in entropy. Question 4 asks us to identify the statement that violates the second law of thermodynamics. Statement D is the incorrect one. For a process to be spontaneous, the total entropy change, ds total, must be positive, representing an increase in the entropy of the universe. A negative ds total would mean the process is non-spontaneous. All other statements are consistent with thermodynamic principles. Finally, question 5 is a multi-part calculation of spontaneity. Part A asks for the entropy change of the surroundings. Using the formula and converting units, we find that ds surroundings is positive 2987 JK1 mol 1. It's positive because the reaction is highly exothermic. Part B asks for the total entropy change. Summing the system and surroundings entropy changes, we get positive 2715 JK1 mol 1. Part C asks about the spontaneity. Since the total entropy change is a large positive number, the combustion of methane is a highly spontaneous process at 298 K. Thank you for watching this detailed lesson on entropy and spontaneity. Let's briefly recap what we have accomplished. We began by defining spontaneity and distinguished it from reaction rate, or kinetics. We saw that the universe has a natural tendency toward states of higher entropy. Our primary objective was to understand the second law of thermodynamics, which provides the ultimate criterion for whether a reaction will proceed spontaneously. We broke this down by first exploring entropy, S, at the molecular level, defining it as a measure of the dispersal of energy and matter, and calculating it using the formula S equals Kb ln W. We learned how to predict the sign of entropy changes, ds, by observing changes in physical state and the number of gas moles. We then practiced calculating ds system using standard entropy values from the data booklet. We then introduced the crucial role of the surroundings, which led us to the second law of thermodynamics. We learned to calculate the entropy change of the surroundings using the enthalpy change and absolute temperature. Finally, we combined these concepts to calculate the total entropy change, ds total. This allowed us to determine the spontaneity of a process based on the simple rule. If ds total is positive, the process is spontaneous. Mastering these concepts is fundamental for success in IB chemistry. If you are seeking expert, personalized tuition to further strengthen your understanding and problem-solving skills in IB A-Level or IGCSE, contact our tutors. Our experienced tutors are ready to support your academic journey.